Hi. Um, okay. My name is Shuhui Li, and I will be presenting on spin-orbit torque enhancement in copper interlayer topological insulator perpendicular magnetic structures. So, first of all, I'd like to start off with an overview of this work. So, as the title suggests, what we are looking at is the insertion of an interlayer into a ferromagnet and topological insulator stack. And specifically, the ferromagnet is perpendicular and isotropic PMA. So what we find is that there is a large spin Hall angle of 65 when we add the copper interlayer, which is a very it's a huge number. It's a huge spin Hall angle. So we wanted to investigate the reason for this. So this work is about that. And we find that the Rashba spin-orbit coupling is significantly enhanced when we add a copper interlayer, as well as the crystalline growth of bismuth antimony in the 012 phase is actually the most crystalline with the copper interlayer. So the combination of the surface states and the spin-orbit coupling actually provides this large spin Hall angle that produces a device that can potentially be used in industrial application. So as a background, I'll give you some background about topological insulators. Here, this is an illustration of a Dirac cone in momentum space. So three-dimensional topological insulators have Dirac cones on there, especially bismuth antimony, which is the topological insulator that we are dealing with in our work. It was the first theoretically predicted and experimentally realized three-dimensional topological insulator in which there are characteristic chiral edge states that I illustrate here. There is a characteristic spin momentum locking as a result of these edge states that are induced as a result of the bulk band inversion in momentum space. So particularly, bismuth antimony has been found to have at least 3 Dirac cones in momentum space. So ideally, we would like to increase the number of Dirac cones, and so we would like to enhance the crystallinity of bismuth antimony 012 in our topological insulator stack when we grow it. So what we did was we grew. Interestingly, we added an interlayer to study the effects of this interlayer in a PMA system. We used harmonic Hall technique. We also did XRD, and we calculated the band structure via the GGA-PBE method. And we also used the Vienna ab initio assimilation package. So here's the main result. We see by varying the interlayer materials, we actually see the best performance of spin charge conversion efficiency in copper. In fact, there's a 6 times increase in the spin Hall angle between the case where there is no interlayer and to the case where we add 7 nanometers of copper at the interface. We also see that the crystallinity is improved the most when we have a copper interlayer. The bismuth antimony 012 crystalline phase grows the most, or the best, and there are the most number of domains. Which translates to a larger number of surface states when you integrate across the surface, which means a larger number of interactions with the ferromagnet to produce a larger spin transfer torque. And so this is one reason for the result. Second reason is the doping that occurs at the interface. Here we see that where there are no copper atoms, there is some spin orbit, Rashba spin effect, Rashba spin splitting. So here on the left-hand corner, this shows the band inversion in bismuth antimony. Now when we interface copper with the bismuth antimony, we actually see that it's energetically favorable for doping to occur. So what happens is that the copper actually dopes itself into the bismuth antimony surface, and the DFT results actually show that the Rashba effect, the spin splitting, is actually pronounced when copper begins to start doping into the bismuth antimony surface. So that translates to this model, which illustrates what is going on. Without any copper dopant, there is some spin splitting. Now, as we add copper, as copper dopes itself into the bismuth antimony surface as a result of being adjacent to the bismuth antimony material, there is actually a 2D surface at the interface that is formed with the enhanced Rashba spin orbit coupling. And this translates to a larger spin Hall effect. And because of the large spin diffusion length in copper, the larger spin Hall effect actually gets conducted downwards into the ferromagnet and is preserved. So in conclusion, we study different interlayer materials and its effect on the spin charge conversion efficiency. In this stack, we actually see that copper performs the best. The reason being that copper has a larger number of surface states, induces a larger number of surface states in the growth of bismuth antimony 012 phase. It grows better when a copper interlayer is added below it. And additionally, there is some doping that occurs that enhances the Rashba spin orbit coupling. And this resulted in an enhancement in the spin Hall effect. And so these two major reasons are causing the effect that we measure. And in conclusion, we also measure the largest known experimental spin Hall angle for bismuth antimony grown on silicon substrates. And we measure a spin Hall angle of 65. So that's all. Thank you very much. Thank you very much for your attention.